Okay. So we left off last class talking about different probability laws. We kind of went over Bayes' theorem. So we're going to kind of take a little bit of a different direction, but use a lot of things that we've already talked about. So today will honestly should be a fairly easy class. The first part will seem almost like review. I'll be mentioning a lot of old concepts, and then we'll kind of jump into some newer stuff towards the end and kind of pick up on that on Wednesday. So we'll get going here. So we've kind of thought about this a little bit with experiments where we said the experiment has all these different possible outcomes. We don't know which one it's going to be, right? We want to find the probabilities of each of, like, what's the probability that each of those outcomes occurs, right? So we're going to set this up in a slightly different context now, talking about random variables. So a random variable is something we can record the response for, but it's really just an outcome of some experiment, right? It could be as simply, I guess maybe the audio is not working. Okay, here, let me test. Is that better? Sound all right? Okay, hopefully. To some people I was sounding okay, but sometimes I got to reset that audio. So if we don't have, right, we don't know what the outcome is going to be, we're going to record that, right? So this random variable is some variable that we're recording the response for. Oops. It's going to be very similar to just a regular quantitative variable. We can see a discrete or we can see continuous, right? So the way that we're going to write this is our random variable we'll write as capital X. So just capital X, it's the X variable. That's how we're going to notate it. So capital X is our random variable, and then every time we run this experiment or we see kind of this outcome, we'll notate that with lowercase x, and then x1 was the first outcome we saw, x2 was the second outcome, so on and so forth. Right? So nothing too crazy yet. Right? So discrete random variables, it's basically just a discrete variable that we didn't know what the outcome was going to be prior to running the experiment. Right? So we said usually then with these discrete variables, it's a finite number of responses or a smaller number of responses. Right? So this could be, oops. There we go. We've got our number line, right? We can see 0, 4, 8. We're not going to be able to see 6.3, okay? Really, we can think of these. These are going to be variables where the only response we can see is an integer. Right? We've already kind of talked about these before. How many times a week do you do a certain activity? How many children live in the household? Right? We kind of had some of these examples when we talked about discrete variables the first time. Continuous random variables are going to be where we could see any response. So we go back to the number line. Now we can see 6.35. Think about income, interest rates. Like, this is basically just a review of what we talked about before. Okay. Now we're not going to deal with continuous random variables until after that first exam. Until after the first exam. So say sometimes we introduce one of them, but I think we'll probably hold off and then wait till after the exam. So we're primarily going to be focusing for this exam on these discrete random variables, okay? So we'll be thinking about integer responses. Okay? So we'll go past here. So we've already talked about this before, right? Family size, the number of children or dependents in the household, right? That's going to be discrete. Distance, right? That's going to be continuous. We could measure that out to whatever decimal we want. And then a lot of times with these discrete variables, we'll start to see these kind of qualitative variables that we're turning into quantitative. Right? So do you own a dog or a cat? The responses would be, I own neither, only a dog, only a cat, or I own both types of animals. Right? So here we can just code those as a number. 1 represents no pet, 2 represents only a dog, so on and so forth. So this is an example where we took a qualitative variable, right? The response is qualitative, but we're just assigning it a numerical value, and so now we have a discrete value, a discrete variable. And we'll see different examples of these as we kind of work through. But this is kind of something we may not have seen yet, right? Turning this qualitative into a quantitative variable. So what we want is when we have these discrete random variables, we want to know how likely are these different outcomes, right? If I'm thinking about here, how likely is it? What's the probability if I ask somebody at random that they own no pet or I see a 1? What's the probability I see a 1 response? What's the probability they only own a cat? What's the probability I see a 3, right? That's what we want. And once we have all those probabilities, we'll call that a probability distribution. Right? This is essentially what we were doing when we were creating those histograms, right? Once we got to the relative frequencies, we had the probability of seeing every single possible response. So hopefully on that Excel assignment, right, there we forced into bins, so it wasn't truly discrete. But if you think about instead of bins, if we had 8 individual responses and we just found the probability of each one, that's essentially what we were doing. Right? So we then have our probability distribution that tells us the probability of seeing every possible outcome. Right? Usually we can put this in a table, in a graph. A lot of times we'll have a function for this. I think it might be jumping the gun to the next slide or 2 slides ahead, but the function we're going to call is a probability mass function. We'll go over that here in just a second, but we want to end up arriving and having this distribution. Okay? Oh, yeah, there it is. So the probability mass function, right, is going to be some function. Usually we would write this like f of x. Well, this is kind of p of x. Like it's giving us probabilities, but it's still a function that's telling us the probabilities of seeing different outcomes for this random variable x. Okay? So we plug a certain response into this function. So let's say we think about the number of kids in a household. Maybe I want to know the probability that if I ask somebody at random they have 3 kids. I plug a 3 into this equation, and that probability mass function would spit out at me the probability I see 3, right, as the response for that variable. Okay? So the way that we'll think about this is, I just said, I can plug in different values of x, and this function will give me the probability that the random variable x is equal to that specific response. So a lot of the times this here would be like a 1 or a 2 or a 3. Like we just plug in the integer values that we're interested in, and we can end up getting that probability. Right? Well, once I have these pairs, what could I do? Well, I've got the x value here. If I treat my probability as the y value, it's almost just like what we do with histograms, because I have a probability, just like I had a relative frequency. I can plot that on my y-axis and then just go through and say, okay, the response of 0. Create a bin of 0. Draw a bar up to whatever the probability I see 0 is. Then look at the next response, 1. Have 1 as kind of my second bin or my second category there. And then draw a bar up to wherever the probability that I see 1 is, right? And just kind of go through and just build a bar for each one of those. And then I end up with my probability distribution at the end, right? So this probability mass function allows us to build that probability distribution. But this is basically what we're doing with histograms. Or very similar, but it's said now we only have discrete responses. So these probabilities that this function is going to spit out at us, we know a couple things about them. First of all, the lowest it can be is 0, right? We can never see negative probabilities. And then the highest it could be, although this would be a very uninteresting example, but the highest it could be is a probability of 1, right? But typically it's going to be somewhere in that range. Okay? Now, just like with relative frequencies, or just like when we were thinking about the entire experimental outcome space, if I add the probabilities of every single outcome up, right, as long as I've covered every single possible outcome, those probabilities should add up to 1, right? So if I go through, start with the very first outcome I could see, find the probability, then go to the second, find that probability, all the way to the very last possible outcome, n, and then I add all those probabilities up, they should add up to 1. I think once we get to some examples, I'll kind of explain this a little bit more. It'll make a little more sense intuitively why these have to add up to 1. Right? But we've kind of already talked about this just in a slightly different context before. Okay? I'm going a little quick. Like I said, a lot of this is review, and I think hopefully once we start working some problems, it won't be too bad. Any questions at this point? Okay with this? Okay. So we did this a while ago, and I kind of did it in Excel, but we had this idea of cumulative, right? So we said the cumulative frequency or relative frequency was take the frequency or relative frequency of the bin you're looking at and add to it every possible, all the bins below it, right? So the idea here is going to be similar, okay? So if I want to use that number of kids example, and I said, well, if you plug 3 into the probability mass function, it'll tell you the probability of seeing 3 kids in a household. All the cumulative mass function is going to do is it's going to tell you the probability of seeing that outcome or anything lower than it. So in the kids example, that would be like if I had my cumulative mass function, if I plugged a 3 into it, it'd be the probability of seeing 3 kids in a household or fewer. So I could see 3 or 2 or 1 or 0. So all we're doing there is taking the probability of every outcome that would fit this criteria, right? X being less than 3. I'd find the probability X is equal to 3, plus the probability X is equal to 2, plus probability it's equal to 1, plus the probability it's equal to 0. And that's what the cumulative mass function will do for us. So as X gets closer to 0, my cumulative mass function gets closer to 0 as well. As the X value gets larger and larger, my cumulative mass function starts to approach the value of 1, right? Once I get to the highest possible outcome I could see, my cumulative mass function actually should be 1, right? Because essentially, what the cumulative mass function is doing is it's taking the probability of seeing that highest outcome or anything below it. Well, that's every possible outcome. And we just said, if we add up the probability of every possible outcome, they have to add up to 1. So our cumulative mass function ends up being 1 once we get to that highest possible value we could see. Okay. Oops. So let me try something here. Oops. Come back up here. There we go. Instead of kind of switching, because I know it takes a little bit of time. Oh, so I'm still going to switch for us here in class. So. See if I can get this here. All right. We'll kind of work along here. There we go. I'll try to write this kind of big. So let's say I just want to kind of paint this just so we can kind of see it. But if I want the cumulative mass function, right, for the probability that X is less than or equal to 3. Okay? Well, what I can think about is I could actually rewrite this, right? What this is really saying is, what's the probability that X is equal to 3, or, right, using our union, X is equal to 2, or X is equal to 1, or X is equal to 0. All right, kind of ran off there, but you get the idea. Well, anytime we're looking for unions, what was the rule we had for that? You just take the probability of each event, and then you subtract what you double counted, or you subtract the intersection. Well, here what's interesting is, could I ever see exactly 3 and exactly 2 people or 2 children in a household? No, if I'm saying just exactly, right, one of those has to be true. There are either 2 kids exactly, or there's 3 kids exactly, or there's 1 kid exactly. So there's no intersections between any of these events. So essentially, all we have to do is add the probability of those events together, right? Or add them up, I guess I should say. Right? So really, that's when I said the cumulative mass function, all you're doing is taking the probability of the highest outcome that you want to know for that cumulative mass function, and then add to it the probability of every outcome below it. Okay? Any questions on that? So kind of the key there was that we know the intersections are 0, right? We're only going to see one of these outcomes at a time. Excuse me. Okay. Let's come down here. So I had this, I actually grabbed this data from something that wasn't his variable, then I thought this variable would be more interesting to talk about. So you can kind of imagine if we're trying to put this in more of a business sense. So let's say I've got some company, and they're relatively small, but I'm looking at their number of hires kind of every year. And I'm seeing how many times in the last 35 years did they have, and I have wins here because I changed the example. Hold on. Make sure this lines up. There we go. The number of new hires, right? How many years did they have exactly 0 new hires? There was actually no years in which they hired no one. How many years did they have 1 new hire? 2 years, they only hired exactly 1 person. How many years did they have 5 new hires? Well, there were 4 years where they had 5 new hires, right? Maybe business was better in those years. And you can kind of think about, if we go down the list, you can see the different frequencies of the different number of hires. Once we get to these higher values, we start seeing zeros, right? They were a relatively small company. There was no year in which they actually hired 10 or more people, okay? But they still are possible outcomes, right? You still could see those in the future. Just for the last 35 years, those frequencies are 0. So all we're going to really do is take this data and assign the probabilities. We're essentially creating that probability mass function. we're going to assign the probabilities for these different outcomes based off of some historical data. How could I turn these frequencies into probabilities pretty easily? Just divide by, yeah, my total number of observations, or here that was what, 35 years? Okay. So I go ahead and do that, right? Turn these all into probabilities. If I add these probabilities up, what should I get? That value of 1, right? Because I have to see one of these values, right? So if I add these probabilities up, I should end up getting 1, okay? Any questions on those? It shouldn't be too bad yet. So all we're really doing there is, like, before we were calling relative frequencies, we're now going to just use those relative frequencies as our probabilities of these different outcomes. Right? So this is kind of like I always have a hard empirically assigning those probabilities like we talked about. I could then put those into a graph, right? Just take the different outcomes, plot as the y value that probability, right? And I'd end up with a little bar graph that kind of looks like the histograms we were doing, but here, right, they're not bins, they're actually just individual responses. And I can kind of get an idea about the distribution of the data here. You know, most of it is kind of laying in the middle here, where I see the most common responses are 3 and 4. I never see any responses past 10. You know, you just kind of get a quick idea with this visual. Okay? Any questions on that before we keep moving? So, you know, if we're looking at this, we probably say, you know, the company on average probably hires, I don't know, around 4 or 5 people. Right? But how can we actually find what that average is? Right? So when we have a variable that we don't know what the outcome is going to be, and we're like essentially like kind of predicting the future, we're going to call the mean, is basically another word for it, is the expected value. Okay? So I'll probably often reference it as the mean because that just makes it easier. But you know, the correct terminology really should be expected value, because we're projecting what the kind of average outcome is, right? So we'll write that as kind of the mean of this random variable x, right? Or you can think about it as the expected value of x, right? So how do we find this expected value? Okay. I'll go through the equation, then I'll show you a little small example. So all you have to do is go through every possible outcome, multiply that outcome by the probability it occurs, and add them all up. Right? So this should look kind of familiar. This looks kind of like a what? Weighted mean, right? We've got our different values. We then have our weights, which are just probabilities now. Right? Why don't we have a denominator? Well, what would the sum of our, if our probabilities are our weights, what should the sum of our weights be? If I was going across every possible outcome and adding up all the probabilities, those probabilities should add up to, yeah, 1. Right? So really it's like a weighted mean where the sum of our frequencies, or the sum of our weights are now probabilities. Those probabilities will just add up to 1, right? Our frequencies or our weights here will just add up to 1. So it makes it a little bit easier. So it shouldn't be too bad. I'll go to like a quick example here. So I want to make it big, so I'll switch this over. We'll see if it gets mad at me. Yeah, it's going to get mad at me. I figured it would. Stop share. Hold on. There we go. So, all right. Let's think about, I always kind of like to use this example, but the math is difficult for me to do in the head, so we will see. So let's say I buy a lottery ticket, right? What are the two like possible outcomes? Let's say there's no like intermediate prizes. We'll do a simple lottery like a, what do they call? The 50-50 raffles. Like if you're from Indiana, I'm sure you've seen those like at a basketball game or something like that. They always want to raise money that way. So if I kind of buy the ticket and lose, right? I don't win. Maybe let's say it was $1, right? So my one possible outcome I could see is that I lose, I guess, $1 here. Let's say I win, and I don't know, the prize pool ends up being $500. Right? But going into it, I know, you know, the probability based off of like historical 50-50 raffles, the probability that I actually win maybe is something like, I don't know, 0.001 or 0.1% chance of winning, which would mean the probability that I lose, right, is 0.999. Right? So if I'm trying to figure out the expected value of this lottery that I'm playing, right, what I'm doing is I'm taking each possible outcome and multiplying them by the probability they occur and then adding them up. So really all I'm doing is saying, look, there's a 99.9% chance I lose $1 playing this raffle. Right? There's a 0.1% chance, or probably a 0.001, that I win the $500 prize. Right? So my expected value, or my expected payoff, is going to be the sum of those two products. So I don't know, if we work this out, here we could do this. I'm kind of interested in what it is. So let's go, I'll just pull up Excel real quick so I can do the math. So yeah, 0.999 times -1 plus 0.001 times 500, right? So my payoff is still about we'll call that 0.5, right? So if I do this math, I get about -0.50, which is really saying my expected payout from playing this raffle is -50 cents, right? On average, if I buy a raffle ticket, I'm going to lose 50 cents. Now, it seems kind of weird because I can't actually lose 50 cents, right? All I can do is lose $1 or win actually, to make this make more sense, I should have called this 501, right? Sorry, 499, because I had to pay $1 to play, but you get the idea, right? So I guess technically here, the way I said it, the prize pool was $501. So I ended up winning 500. Now, so I never can see, right, my expected value, right? It's not one of the two possible outcomes, but it's giving me some idea of, on average, if I played this raffle over and over, kind of what would my average winnings be? And here, you'd lose on average 50 cents, right? So this is like not even near like a real lottery. Like, you know, if you're thinking about like the mega ones where like this is like 500 million, you know, this probability is so incredibly low, but if you work it out, you always find that, you know, these lottery companies like that, or the state runs these lotteries because they're not losing money, right? On average, you're the one losing money, and then they're kind of gaining from you playing, right? Sorry, it's kind of a quick, like really easy example to think about if I only had two possible outcomes, right? Discrete, and how I could use those probabilities to find my expected value, right? But when we find that expected value with these discrete random variables, we won't actually be able to observe that specific outcome. So if we go back here, I think the example that I was showing you, oops, there it goes. Yeah, so right here, we could find the mean number of new hires by going through every possible outcome, multiplying it by its probability. So 0 times 0 plus 1 times 0.06 plus 2 times 0.03 plus 3 times 0.2, all the way to the very last outcome. Right? So if I go ahead and do that, right, it's going to look a little messy, but it's really not that bad. Right? I end up getting about 5.14. So, you know, just looking at that distribution, we said it's probably the mean is right around 4 or 5. Sure enough, it's about 5.14. And, you know, we can't actually see that as an outcome, right? We either see 5 new hires or 6 new hires, right? But on average, over the last 35 years, the number of new hires we see is 5.14, right? So it's a little bit weird in that we're getting a value that we can't actually observe, but it is telling us, like, if this is the mean, what would be kind of the most likely outcomes for me to see, right? Well, the two nearest outcomes to this, so 5 and 6 would be the most likely outcomes we see here. For thinking about kind of, or at least like for that mean, like where the middle part of the data is at. And, you know, you can think about it, you know, these values like 3 and 4, they had higher weights, so they influenced that mean or that expected value a little bit more than observations like, oh, I don't know, like 2 didn't affect it very much, right, because its probability was really low. 10, 11, and 12 didn't affect this mean at all because their weights were 0. Right? So it's basically a weighted mean painted in a slightly different context, and honestly actually easier because the sum of our weights now, that denominator is always 1. Okay? So if I can do an expected value, I can also do a variance, right? It's going to be pretty easy, very, very similar to that weighted variance. We'll just take the deviation from that expected value or that mean, square it, and multiply it by the weight, which our weights are now probabilities. So then I do this for every observation, add them all up. That's my variance because I don't have a denominator because the weights are probabilities and the sum of my weights should just be 1. Just like always, standard deviation. Once I find my variance, how do I get my standard deviation? I simply take that square root, okay? So same principles apply as before. Really, it's just a weighted variance, but a little bit easier, right? We don't have a denominator to worry about now, okay? Any questions on this before we keep moving? So if I want to do that with my data set, right, I'll take that 5.14, which was the mean, take the first outcome of 0, 0 minus that mean squared, times the probability 0 occurs. Well, honestly, that one's not very interesting because 0 times anything is 0. But we'll go to the next outcome, 1 minus that mean of 5.14 squared, multiply by the probability that we see a 1 occur. Go through and do that for every observation, add them all up, and we have the variance. Like I said, there isn't really a whole lot new here. It's basically weighted variance just using probabilities. Okay? Any questions here? So, you know, instead of getting like a mean and a variance of a variable or looking at like where the average or where the central tendency or where the dispersion of the variable is, we're just looking at the central tendency and the dispersion of this random variable where we don't know what the outcome is going to be yet. Okay? So let's work through another pretty kind of easy example, maybe something more like you would see on a quiz. So let's say that you could see, you know, different, I don't know, there's some big trading company and they're giving out bonus amounts, and I don't know, it was a wild example, but we're just going to say these are millions, right? So they either get no bonus, $3 million, $6 million, or $10 million, right? So what would the mean of this discrete random variable be? Well, if I'm just looking at this, you know, what are the most likely outcomes here? 3 and 6 million, right? And then kind of 10 and 0 or some likelihood of occurring. So I'm thinking it's probably going to be somewhere in between 3 and 6, just based off of this. You know, A and B aren't within that range. C and D, I can't determine which one it's going to be just by looking. I mean, at least me, I can't envision what these numbers are going to end up being. But, you know, if I look at the most likely outcomes, it's probably going to be somewhere between 3 and 6. A seems way too low, right? If A was the mean or the expected value, the probability of seeing a 0 would have to be much, much higher, right? Probably like 0.8 or 0.9 or something. So how can we go ahead and like calculate this, right? Well, all we're going to do is go through each outcome, multiply it by the probability it occurs, and add them up. So 10 times 0.15, I think that's what, 1.5 million. 6 times 0.25, it's actually also 1.5, so we're up at 3 million. 3 times 0.4, it's 1.2, so 4.2 million. 0 times 0.2 is 0, so 4.2 is what those all added up to, right? Just took each outcome, multiplied it by the probability it occurred, and added them all up. Oops. And if we did that, we end up with 4.2 million there, okay? I know I just kind of like said that out loud. So are there any questions on exactly what I was doing there? All I was doing, if it helps you to think about this, see if it'll let me add. I'm just going to select this one column here. Go to insert column to the right. There we go. So I could do the intermediate step where I just take each one of these outcomes, I didn't mean to capitalize that, and multiply it by the probability. So if I do that here, I get 1.5 million, 1.5 million, 1.2, and 0. Now I just add these all up, and that's how I got that 4.2. Okay? So if it helps, just create that column right next to the data. Okay? All right. What if I wanted to find the variance, right? So if I remember that the mean is 4.2, right? How would I go through and calculate the variance for this example? Well, I would take each outcome. So if I take the first one as 10, subtract that mean of 4.2, square that value, and then multiply it by the probability that I saw that 10 occur. Do that for every observation, and then add them all up. But if I look at these answers right away, are there any answers I can rule out right away here? Yeah, why can I rule out B? Yeah, when I'm looking at the variance, we said, what's the lowest value that an observation can add to the variance? Well, that would be an observation that doesn't deviate from the mean at all. So the lowest number you could add is a 0. So the lowest the variance can be is 0, which if the variance was 0, we'll talk about in a second. But so the lowest it could be is 0, so we know that we can't see negative values, right? It has to be some positive value. If I had a weighted, the variance of a discrete random variable be 0, what would that actually look like? What would that be? What would your outcomes look like there? Yep, so they'd all be the same. So with this discrete random variable, that would mean that the only outcome you could see would be one specific value, and the probability you saw that value would be 1, right? There would only be one outcome you could see, and you would see it with certainty. So it's very unlikely we see a variance of 0, right? It's probably something a little bit higher than that, okay? Otherwise, it's not a very interesting example. Yeah?
The variance one more time.
Yeah.
So you add them all up for the first one, it'd be 4.2 minus 10 times 0.15.
Yeah, we'll go through the same thing that we just did for the mean there, right? I gotta make that bigger. So we'll go through, take the outcome, subtract the mean, square it, and then multiply it by the probability occurs. Let me make this even a little bit wider here, so hopefully we can get this all on, not quite on one line. Make this smaller. There we go. Perfect. So we'll take that value of 10, right, that first outcome, subtract the mean, which was 4.2, square that value, and then multiply it by the probability we saw that 10 occur. Okay. I'll even put a little space in here so you can see it. We basically go through and do that for every observation and then add them all up. And usually we'd have to divide by the sum of our weights, but once again, here the sum of our weights should hopefully be 1, right? Our probability should always add up to 1. Does that answer your question? Yep. Yeah, so that's what it would look like if you wanted to kind of do this line by line. Okay. Any other questions at this point? This shouldn't be too bad. This is really stuff we've kind of already done, just with a different kind of terminology. Also, does anybody recognize this movie? Have any of you guys seen this? You're in the business school. So this is called The Big Short. You should all go watch it. First of all, it's a really good movie. But like, it kind of chronicles what happened with the mortgage-backed bond kind of bubble and how that kind of burst and the kind of the fallout of all that. But from like kind of a company kind of viewpoint, it does a really good job of just like explaining it like in essentially layman's terms. And you probably would understand even more of it, kind of coming from a business school. I always tell people, like, my sister liked this movie. I remember I ended up somehow seeing it with her and her husband, and she's like the most bohemian hippie, like doesn't know anything about finance, numbers, wants nothing to do with numbers, and she liked it. So it's a good movie, and it kind of explains what's going on, or what was going on at that time. So I always like to bring that up there. Okay, so those examples I was just giving you are really like easy, I guess, but the probability mass function wasn't following a certain pattern or rule, right? It wasn't really a function. It was based off of data. Like, we were empirically assigning these probabilities to say there was no like functional form, right? The function just was, if you plug in a 3 here, I can tell you the probability of seeing a 3 is 0.2. But like, there was no like a plus b times x squared. You know, there's no actual functional form. So we're now going to deal with some examples where we actually have a functional form. Okay? So let's say I'm going to run an experiment, an identical experiment, n number of times, right? So this could be something as simple as flipping a coin. I'm going to flip this coin 50 times. Right? What's the probability if I flip that coin once, the probability it comes up heads is just 0.5. So I know the probability that on any one coin flip I get a heads is 0.5. If I flip a coin, and instead of 50, I'll make it easier. Let's say I flip a coin 100 times, right? I might want to know, well, what's the probability that I see exactly 50 of them come up heads? But also, it could be that out of those 100 flips, I just happen to get 60 heads, right? So what's the probability I get 60? I know that on average, if I flip a coin 100 times, on average, I'll probably see about 50 of them come up heads. But there, I could see 60, right? I could see 60 of the 100. So what's the probability I do see 60 out of the 100? And it's very unlikely, but there is a world in which in 100 coin flips, I flip it 100 times and get all 100 heads. Very, very unlikely, probably a really low probability, but it still is possible. So what would the probability be that I flip all 100 coin flips and they all come up heads, right? I can use this binomial distribution to find those probabilities, okay? So we've got n number of trials. The way I kind of set this up with a coin, in a more general context, it's not heads and tails. It's just going to be there's two outcomes, and we'll call them the success and the failure, right? If it's easier, you can think about it as like binary, 1, 0, right? There's something that we're looking for, that's the success, and the failure is just not seeing that. So if I'm thinking about flipping a coin, my success was seeing it come up heads. The failure is seeing it come up tails. Okay? I kind of use the coin example because what also has to be true for a binomial distribution example is the probability of success is the same for any one trial. So each coin flip, the probability I get a heads is 0.5, right? That doesn't change across the 100 coin flips that I do. Right? Excuse me. The trials have to be independent, right? So the first coin flip can't depend on the second coin flip can't depend on the outcome of the first coin flip, and so on and so forth. So I'll never try to like trick you with violating this principle, but all the examples we'll think about that are binomial, the trials are independent. Okay? Oops. So really we're setting this up as, I kind of already alluded to this, but how many, what's the likelihood that I see 50 of the 100 coin flips come up heads? What's the likelihood I see 60 out of the 100, right? Or what's the probability, right? That's what we're going to be looking for, okay? So out of n trials, what's the probability of seeing a certain number of successes? X. Oh, there we go. So that binomial function will give us that. It'll tell us those probabilities. Okay? If I plug in, 50 successes out of 100 trials into that equation, it'll spit back out at me the probability that I see 50 out of 100 be successes. That equation is going to be kind of nasty, right? Or at least until we get used to it. So we'll walk through this equation pretty slow. Some of this you probably haven't seen before. I think this part over here isn't too bad, right? We basically just have things being raised to a certain power. So the P in this equation is that underlying probability of success on any one trial. So in the coin flip example, this P would be 0.5, right? The probability of success or seeing a heads on any one coin flip is 0.5. So that was our P. X is the number of successes you're interested in finding the probability of. So if I flip the coin 100 times and I want to know what's the probability it's 60 of them come up heads, my X would be 60. That's the number of successes I'm interested in finding the probability of. And then finally, N, well, that's just our number of trials, right? Because if I flip a coin 100 times, the probability I see 60 out of 100 come up heads is going to be much different than if I want to find the probability I see 60 heads out of 1,000 coin flips, right? I mean, so we're going to have to think about N's going to matter here. The number of trials matters as well. So basically, this part of the equation is just things being raised to a power and then multiplied by each other. The part we probably aren't used to is this factorial, right? So this factorial basically means if I say plug a 10 in to that, 10 factorial, take that number and multiply down to 1. So 10 times 9 times 8 times 7 times 6 times 4 times 3 times 2 times 1. If I had 5 factorial, it's just 5 times 4 times 3 times 2 times 1. Right? That's all the factorial means. Okay? So we've talked about what all these things mean. There's like a more formal way of thinking about the factorial, but the way I said it, I think is probably the easiest way to think about it. Take the number that you're looking for the factorial of and then multiply all the way down to 1. Okay? Any questions on this before we keep moving? Okay. So let's just work through an example with some values here. So let's say instead of 100, I want to flip a coin 10 times. Okay. What's the probability? And I know the probability, let's say this is a weighted coin. So the probability this coin comes up heads is only 0.4. Okay. What's the probability that I see exactly 4 of the 10 coin flips come up heads? So what's my n here? What's my number of trials? 10. What's the number of successes I'm looking for the probability of? Yeah, 4. So someone holding it up. And the probability of success, or the probability I see a heads in any one trial, is just that 0.4. Right? So it's really just a matter of identifying those 3 things and then plugging them into our equation. Okay? Now, if you're trying to do this in your calculator, the factorial button on like the TI-83s and stuff, I think it's, there's a math button. It should say like math on it. And then one of the things on top says like PRB or PROB, it's probability. And if you go over that, and then I think it's the 4th one down, you'll have a factorial button. Some calculators, you have, it's one of the buttons. You hit like second, and then it's one of the buttons. Or if anytime you have a PRB button or a math button, that's usually where it lies. Obviously, every calculator is a little different. If you're having problems finding it, email me and let me know, or talk to me on Zoom after class, or talk to me in person, because we want to make sure that you know where that's at in your calculator here really quickly. Okay? But in an example like this, you could probably work it out in your head, right? I mean, or you could enter it in even without the factorial button. You could type in 10 times 9 times 8 times 7 times so on and so forth. The problem is if you try to do it by hand, there is a point, and I think even on the 83s, it's like somewhere in the 60s, your calculator can't do it. It just gives you an error. Right? It says, because I mean, think about it. It's going to be a really large number, right? 60 times 59 times 58 all the way down to 1. A lot of calculators can't handle that. So what if we run into that problem? So I want to show you an example where what happens if you run into one of those problems. So let's say, I think we'll probably end with this, but let's say I had, I don't know. Say I'm flipping a coin 100 times. Oh, actually, this is a good one. I'll point this out. Let's say I'm flipping a coin 100 times, and I want to know what's the probability. So we'll say my n is 100, and I want to find the probability of getting 99 heads. All right? I know this is going to be pretty unlikely, but I'm interested in how unlikely is it. And I know the probability of success will go back to where it's simply a regular coin, it's 0.5. If I start writing out my binomial equation, I'll have n factorial over x factorial n minus x factorial probability of success to the x times 1 minus the probability of success to the n minus x. So this might look a little daunting, but it's actually a pretty easy. I mean, what's 100 minus 99? Yeah, just 1. So don't enter it into your calculator like this if you're doing the math. Like, you can do this math in your head, anything to the 1 power, like that's just the number that it is. So this becomes a lot easier, right? This part, we're like, well, you just told me you can't do 60 factorial on a calculator, right? Yeah, you can. But if I write this out and think about what this is, 100 times 99 times 98 times 97 all the way down to 1. And I'm just writing out this part of the equation right now. And I would divide that by 99 factorial, so 99 times 98 times 97 all the way down to 1, times, what's 100 minus 99? 1. 1 factorial is just 1, but multiplying by 1, it doesn't change anything, so I can almost ignore that. Well, notice what's going to happen here. Everything from 99 down cancels. So even though this looks kind of crazy and I can't enter this into my calculator like this, if I write this out and think about what cancels, all this was saying was 100 divided by 1, right? So this whole thing was really just 100. So anytime you have these really large values, and they're large enough that your calculator can't handle them, it's probably because you can do some simple cancellation if you just write out what that factorial looks like, okay? Any questions on that? Does that make sense? Let me make sure there's nothing here. The other thing I want to point out before we get out of here today is, let's say I had an example, and let's say I wanted to know what's the probability that all 100 of those 100 coin flips are tailed or heads, whatever, right? So if I write out that equation, 100 factorial divided by 100 factorial times 100 minus 100, right? And minus x factorial, p to the x times 1 minus p to the n minus x. Well, 100 minus 100, this is just 0. Anything to the 0 power is what value? Do you remember this? Anything to the 0 power is actually just 1. 5 to the 0 power, 105 to the 0 power, they're all just 1, right? So that part, kind of, we can ignore it because we multiply anything by 1, it's the same value. This will be something, 0.5 to the 100 will be something, but what happens over here? 100 factorial and 100 factorial cancel. What's 100 minus 100? 0, so 0 factorial. It's a little bit weird, but with factorials, 0 factorial is actually equal to 1. Okay? So this is a rule of factorials. If we want to go deeper into it, we can go into some of the kind of mathematical proof side, but for the sake of how we're going to use it, let's just remember that 0 factorial is equal to 1, okay? So if that's the case, this equation, this whole thing, well, this is just, this canceled, anything times 1 is 1. The only thing that we're really left with is that, right? It was really like 1 times that times 1. And this kind of makes sense for things we've talked about in the past, because if I flip a coin 100 times and the probability every time of seeing a heads is 0.5, right? They're independent events. We said if they're independent events, the probability I see A and B is just the probability of A times the probability of B. So the probability I see a heads on the first flip and on the second and on the third and on the fourth and on the fifth, all the way up to the last one, well, that's just 0.5 times 0.5, 0.5 times itself 100 times, or 0.5 to the 100 power, right? So our binomial equation, when we're looking for all successes, basically just becomes that rule of independence. We're finding the intersection of those events. You can just take the probability of every event and multiply by itself. Okay. Oh, this is off the screen, sorry. Any questions over any of that? So I'm kind of setting us up for next class, not really completing kind of the full discussion of the binomial. We'll kind of keep working. We'll see some different things. We'll talk about doing some cumulative stuff with the probability, cumulative stuff with the binomial equation. And I'll probably show you how it works. I think I have here. Yeah, we'll look at means. We'll talk about it in Excel. But that will all be kind of next class. I'm going to put up, this is kind of a little bit of a ways off, but I'm going to start putting up some practice materials for the upcoming exam. So this binomial we'll talk about, and then we'll have one more distribution, which is the Poisson we'll talk about this week. But really after this week, and there'll kind of be no new material. We'll kind of just be reviewing for that exam next week. I'll put up the next Connect and the next Excel assignment. So those will be due at the end of next week. So I would suggest highly working on them this week, even though the due date isn't this week. You'll be able to, the Excel, you'll be able to work through almost all of it. After Wednesday, you'll be able to get all of it done, but not 80% of it you'll be able to currently work on. And then that Connect will probably be about, after what we did today, will probably be about 60, 70% of the material we covered for that. So I would start working on those early, get those out of the way. next week, we'll just be doing some review, but also those homeworks are going to be good review to start kind of going over the more recent material. Okay. All right, I'll get an online quiz up today as well. That'll be due before we meet on Wednesday. Other than that, stay safe, especially if you're driving. I think the roads are supposed to be pretty bad, so we'll see you guys on Wednesday.